Hey guys, Mr. Hallman here with our second lesson on factoring. This week we're going to take a look at another way of factoring because, as we talked about last week, adding, subtracting, multiplying polynomials all follow the same basic process. But when it comes to dividing, we don't usually divide. Instead, we think about this process of factoring, which is we take the expression and we break it down into the factors or the numbers that we would multiply together to get that expression. That's different than division because when we divide, we actually have some starting point with which we're going to divide by. Here with factoring, we don't know what our ending answer is going to end up being. So we have to kind of work in reverse. And we talked about the multiple ways that we can do this. One of the first ways that we can factor was by using the GCF. So we have an example here where we're using the GCF, or the greatest common factor, and we're going to look for our coefficients and our variable term GCFs. We're going to factor that out, and then the leftover expression will end up being in parentheses, and it's kind of like reverse distributing. So go ahead and pause the video if you want to try example 1 here, which is 16m to the third n to the fourth minus 12m to the fourth n to the third plus 20m to the fifth n squared plus 4m squared n. Once you think you have the GCF and you have the leftover factors, go ahead and start the video again and let's check our answers. Alright, so if we're looking at this expression, I have 16, 12, 20, and 4. It appears that my GCF between those four numbers is going to end up being 4. Oh boy, let's fix that. So our GCF is going to be 4 for the coefficients. For the variables, remember our shortcut for the variable GCF is we want to use the smallest exponent on any like base. So if I look at the m's, we have m to the third, we have m to the fourth, we have m to the fifth, and we have m squared, which means our smallest exponent on the m should be the m squared. Then we're going to do the same thing with the n's. We have n to the fourth, n to the third, n squared, and n, which means our GCF here is just going to be n. So there's our greatest common factor. We have 4m squared n as our GCF for the expression. In parentheses, we're going to have the leftover factors. So what am I left with, or what would I redistribute 4m squared n to get back to the starting point? So if we look at the first term, 16m to the third n to the fourth, we factor out 4m squared. That would leave us with 4m n to the third. Then we look at the next term. We had minus 12m to the fourth n cubed. We factored out the 4m squared n. That means we would be left with 3m squared n squared. Then we look at the third term, 20m to the fifth n squared. We factor it out. We would be left with 5m to the third n. And our last factor, or our last term here, 4m squared n, that entire thing got factored out, which means I can't just forget that there was an extra term here. If I were to redistribute to get back to that, I would have to multiply it by 1. So there is our final answer, 4m squared n times the 4m n to the third minus 3m squared n squared plus 5m to the third n plus 1. And to have a note down here, as you can see, that the GCF method can be used for any type of polynomial. So it doesn't matter if we start with 2 terms, 3 terms, 8 terms, we could possibly use the GCF method for those factors. All right, let's move on to today's lesson. So in example 2 here, we have x squared minus 16, and we're going to be looking for the GCF. Well, if I look at the coefficients, my coefficient on x squared is a 1. And then I have 1 and 16. Well, their GCF is just going to be 1. Then I look at the variable. X squared in my first term, second term doesn't have an x at all. It's just 16. Which means the GCF shouldn't have a variable. It has to have the smallest exponent. And in this case, no x or no variable with the 16 is like x to the 0. So really in this case our GCF is 1. But if I factor out 1, that's really just x squared minus 16, which doesn't change anything that we've done. So instead, what we would see is that this is not factorable by GCF. So the question becomes, what do we do in a case where I can't factor a GCF out? And today we're going to look at our first case where we're not using a GCF, but we're using something else. What we're going to use today to help us factor is what's called perfect squares. And you can see here we have a list of perfect squares, which we've already come across earlier this year when we talked about radicals and squaring numbers and taking square roots. So all of our numbers in red here, the 1, the 4, the 19, 16, 25, 36, and the 49, 64, 81, 100, 121, 144, those are perfect squares. And what that means is that they have a square root, which is a whole number. And the square root is the number that you multiply by itself to get that perfect square. So in this case, if I have 144, 144, when I take the square root, that's going to give me 12, because 12 times 12 gives me 144. So we're going to see that we can factor using these numbers. Aside from just having numbers that are whole numbers that multiply to give us those values, we can also see that these numbers are perfect squares: 1, 4, 9, 16, 25, 36, and so forth. They're perfect squares because we can make arrangements of squares from that amount of terms. So here with 16, I have 4 rows and 4 columns. With 25, I can have 5 rows and 5 columns. So that's another reason we call them perfect squares. They can make a square arrangement out of that many terms. We've also talked a little bit about variables being perfect squares. For example, x squared is a perfect square because it's x times x. We talked about y squared being a perfect square because it is y times y. And even if I have other exponents like n to the 6th, this is a perfect square because, as we can see down here, all even exponents are perfect squares, not because I have exponents that are going to necessarily multiply to give me that, but if I took n to the 3rd times n to the 3rd, remember our exponent rule tells us that we would add those exponents together, which means this would become n to the 3 plus 3, which is n to the 6th. Following that same idea, m to the 20th. That's a perfect square because it is m to the 10th times m to the 10th. Because if I take the 10 plus 10, that gives me 20. So between this and our perfect squares for constants, we can use a new method to help us factor. So let's revisit our example here of x squared minus 16. We knew that there were no GCFs between those two things. Instead, what I can focus on is that x squared is a perfect square because it is x times x. And I know that 16 is a perfect square. 16 is 4 times 4. So the question is, what could I multiply by itself that would give me x squared minus 16? And what it really breaks down into is two binomials. We're going to take this and we're going to split it up so that we have two sets of two terms. And in this case, the x squared, the x and the x, that's going to be the first term in each set of parentheses. And then this 4, which is 16, the square root of 16 is 4, we're going to put the 4's in the second spot in each set of parentheses. Now the key here is when I multiply these, since I'm multiplying two binomials, I would FOIL them. I want the outside and inside terms to cancel out, so I just get x squared from my first multiplication, and I just want the negative 16 from my last multiplication. So what that means is we're going to use one plus sign and one minus sign. So if I were to check this when I go through and FOIL f plus o plus I plus l, I would end up with x squared minus 4x plus 4x and minus 16. And here, the negative 4x and positive 4x, they cancel each other out. So that leaves us with x squared minus 16. That would mean that this is our correct FOIL, and this is our reverse FOIL, and this is the basic setup for any difference of squares. What we're going to do is we're always going to take, if I have a squared minus b squared, no matter what those perfect squares are, it's always going to split into two binomials, and we're always going to put the square root of the first term in the first spot in each set of parentheses. We're going to take the square root of the second term, put it in the second spot of each set of parentheses, and we're going to use one plus sign and one minus sign. So a squared minus b squared will always become a plus b times a minus b. This is our formula for difference of two squares. Let's look at some other examples where we follow this. All right, so here we go. In number 3, we have a squared minus b to the 6th. Again, no GCF between those two things. And I have my reminder here that all even exponents are perfect squares. So what that means is we're going to be able to take b to the 6th and split it up into the same thing twice. So we're going to do the same thing we did in the last example. Focus on the first term, a squared. Well, that becomes a times a. Then we're going to take the b to the 6th. B to the 6th should become b to the 3rd times b to the 3rd. So now what we're going to do is we're going to take those two things and we're going to put them into our binomials here. And we're going to have the a as the first term in each set of parentheses. We're going to have b to the 3rd as the second term in each set of parentheses. And we're going to have one plus and one minus. And again, my check really here, the first multiplication gives me the a squared, a times a. The last multiplication here gives me the b to the 6th, because b to the 3rd times negative b to the 3rd. The check is that when I do the outside plus the inside, if I take a times negative b to the 3rd, that would be negative ab cubed. And then b to the 3rd times a would be positive ab cubed. And they're going to cancel each other out. And that's a good thing, because that would leave us with just the a squared minus b to the 6th. Go ahead and take a look at example 4. If you want to pause it this time, you can try this one on your own. Follow the same idea. Figure out what's our perfect square or square root for the 36m to the 36th. What's our square root for 25n to the 10th? And then set up your two binomials. So go ahead and pause, try it on your own, and then restart when you're ready. Okay, so 36m to the 36th. We want to be careful here. The coefficient should be 6, and it should be m. But I don't want my exponent to be 6, because it's not that 6 plus 6 gives me 36. It would be that 18 plus 18 gives me 36 for the exponents. In the case of the second term, we would have 5n to the 5th and 5n to the 5th. Here it works out that the coefficient square root is the same as what I should use for my exponent because of those values. And now I'm going to set up my two binomials. I'm going to give myself some room here because they're a little bit larger. The first terms are going to be 6m to the 18th in each case. And the second term in each set of parentheses is going to be 5n to the 5th. And we're going to have one plus sign and one minus sign. There's our final answer. Now, you might be saying, does it matter if I put the plus in the first set of parentheses and then the negative in the second set of parentheses? It doesn't really matter. You could have minus and then plus if you wanted. You could switch those. It wouldn't make a difference. You just need to make sure that one is positive, one's negative. Let's take a look at two cases where we want to be careful. In the case of number 5, we have j squared plus k squared. And the first thing you should see here is that we have a plus in between those two perfect squares. Even though j squared becomes j times j, and k squared becomes k times k, there is no way that I could multiply a positive j or a positive k times a negative k and end up with positive k squared like I'm supposed to here. So in this case, we would say that this is either prime or not factorable, because in this case, there is no way that we could multiply j plus k times j plus k or j minus k times j minus k and end up with the middle term canceling out. So in the case of number 5, anytime I see two perfect squares and a plus sign, I should know not factorable. In the case of number 6, we also have an issue. So take a look for a second. What do you think is the issue here? If you said that you think the issue is this exponent here of 9, you would be correct. Again, this is going to be prime or not factorable, because perfect squares for exponents always need to be even exponents. So this is not an even exponent, which means I can't multiply it or add two whole numbers to get that value for the exponent. So those are two cases you want to be careful of. There's something else that we want to be careful of though too, because we're not always going to have two terms or two binomials multiply to give us two terms. In fact, normally we can see here, we found when we learned how to FOIL that two binomials usually multiply to give us a trinomial. So for example, if I had n plus 5 times n plus 5, when I FOIL this and I go through my steps, we would get n squared plus 5n. For the inside, we would get plus 5n. And then we get plus 25. And I can combine my two middle terms here, the 5n and the 5n, to give me a final answer of n squared plus 10n plus 25. What that means is that if I can take two binomials and turn that into a trinomial, as we've seen throughout the year, we should be able to do the opposite. I should be able to take a trinomial and work backwards to get two binomials. And what we call that is reverse FOILing or factoring. So we should be able to sometimes start with three terms and work backwards. And this connects very well to what we just talked about, because if I look at my answer, I'm going to notice something. Here in example 8, I have that answer from the previous example. What I should notice is that my first term is a perfect square. It's n times n. I should notice that my last term is a perfect square. It's 5 times 5. And in this case, I don't want to use opposite signs in my parentheses, because what I should end up for the middle term is 10n. That's going to come from the outside plus the inside multiplications. So what we're going to do is we're going to still use our binomial, and we're still going to use n as the first term in each set of parentheses. I'm going to use 5 as the second term in each set of parentheses. But the key is I want to end up with positive 10n. The way that's going to happen is if I take a positive 5 and a positive 5. So that way my outside multiplication is positive 5n. My inside multiplication is positive 5n. And when I take those and add them together, that gives me positive 10n, which is where this term comes from here. So what we have here is another case where we can use perfect squares to factor, except I'm going to get the same binomial twice. And I can either write that as n plus 5 times n plus 5, or the other way we might write it is using an exponent. We would write n plus 5, the quantity squared, meaning I have that binomial twice. Let's look at another example. Number 9, we get 36v squared minus 12v plus 1. Same idea as what I saw in the last one. My first term here, 36v squared, that's a perfect square. 6v times 6v. My last term, positive 1, that's 1 times 1. Notice how in this case, I'm not really focused on the middle term just yet. The middle term comes after I look at the first and the last term, because it appears that I'm going to split this up where my first term should be 6v in each set of parentheses, and my last term should be 1 in each set of parentheses. But in this case, my middle term, the outside plus the inside, should give me negative 12v. Well, if it's the outside times the inside, that means I want each of these to be negative 6v so that they would add up to negative 12v. The way that we do that, we make these both minus. So I can write 6v minus 1 times 6v minus 1, or 6v minus 1 squared. That would be another way of factoring here with our perfect squares, and we end up with the same binomial twice. Go ahead right now and let's try these last two examples on our own. You want to pause the video, but again, focus on the first and last terms, find the square roots, and in this case, since we're starting with 3 terms, we should end up with the same binomial twice. So go ahead, pause, and restart when you're ready. All right, here we go. First term in number 10, 49t to the 4th. 49 is 7 times 7. T to the 4th is t squared times t squared. The last term, 4, well, that's just 2 times 2. So what we're going to do is we're going to split this up. Same binomial twice. First terms are going to be 7t squared. And our second term in each case is going to be 2. And here, our middle term is positive 28t squared. That comes from the outside plus the inside multiplications. Since it is a positive, that means we want to use 2 plus signs. So it's 7t squared plus 2 times 7t squared plus 2, or 7t squared plus 2, the quantity squared, because I have that binomial twice. Let's look at number 11. Number 11, we have 81m squared for our first term. Perfect square, that's 9m times 9m. Last term, positive 16. That's going to be 4 times 4. So we're going to set up our binomials. First term in each case should be 9m. The second term in each case should be 4 and 4. And here we want to end up with negative 72m. Negative means that both of these signs should be minus. So we get 9m minus 4 times 9m minus 4, or 9m minus 4, the quantity squared. Again, the big key here is that if we are starting with 2 terms, we're going to end up with different signs. So 2 terms means we're going to have 1 plus, 1 minus. If I'm starting with 3 terms, like I just saw in the last 4 examples, that means that I'm going to end up with the same binomials, either both plus signs or both minus signs. So what we need to do is pay attention to what we're starting with to determine which case am I looking at, different signs in the binomials or same signs. That covers our second method of factoring. You're going to see in the IXL and the quizzes this week that we're going to be practicing these things. Next week, we're going to move on to our third method of factoring. Thanks for checking this out. And if you guys have any questions, let me know. Otherwise, I'll see you on Wednesday for our Zoom meeting. Good luck.